So, hello everybody. For y'all that don't know me, my name is Trevor Russell. Today I'm going to be presenting on Cantor sets. So I'm going to start with a brief introduction and history. So, Cantor sets were discovered by Henry John Stephen Smith in 1874. However, they were introduced by the German mathematician George Cantor in 1883. So basically what a Cantor set is it's just basically a set of points on a single line segment. There's a quote about Cantor sets. The standard Cantor set is quite interesting. It is an uncountable, totally disconnected, perfect. Every point is a limit point. Set of Levisieux measure zero. So basically what that means is, as you can see in the descriptions below, Cantor sets contain the union of all real numbers along a set of 0 to 1. So that's further explained a little bit later in the presentation. But as you can see in this point right here, this actually explains it. So the Cantor set has a measure of 0. If you regard the superset C sub n, basically when you plug in 0, 1, and those successive numbers, and then you have a union of all those numbers, then you begin to the set increases in size, and so by that the Cantor set is formed. So we'll move on to the theorem. So Cantor's theorem, so let F be a map from set A to its power set PA. Then the function A implies that the power set A is not surjective. A surjective function is a function F with domain X and codomain Y. If for every point Y in the set Y, there exists at least one point X in the set of X. So basically, for every Y in the set of Y, there's at least one X in the set of X. So as a consequence of that, the cardinality of A is less than the cardinality of the power set of A for any set of A. So the proof for that, Cantor just kind of goes into a brief contradiction of that. So he's supposing to the contrary that F is surjective in order to prove that it is not. He then goes in and provides a counterexample which proves that F cannot be surjective, as you see here. And so that proves that the cardinality of A is less than the cardinality of the power set of A. So the importance and the uses of the Cantor set. So there are a lot of applications for the Cantor set. One being it's used a lot in modern point set topology, which is pretty self-explanatory. It's just plotting the points that are in the Cantor set on a graph. And so that begins to form a fractal when you begin to graph the Cantor set. So I'll have a picture of that in a second. But it's also used in measure theory, which is used a lot in data analytics. So this is just a picture of one of the applications of the Cantor set. It's Sierpinski's triangle. There's the fractal dimension of Sierpinski's triangle is that formula right there, which is very similar, or it lines up with the formula that was previously given for Cantor set. So these are the sources that I used.
Any question? Did you read some articles about fractal?
Yes.
Do you like it?
I did, yeah, it was super cool. A lot of the pictures were like really, really cool. I didn't want to put...
Yeah, pictures are cool, I understand, but you know, the theory.
Oh, I didn't look as much in the theory.
Yeah, that is very huge, you know, branch of math. So,
Yeah.
and there are a lot of applications in computer science.
Mm-hmm.
Yeah, it would be good.